In the previous example, we had an object, we exerted a force on it, it moved, there was work. So the work allowed us to add energy to it. And so it had energy. So it was storing all this work in energy. So how much energy was there? Obviously 70.6 joules for the previous example. But there's another way of looking at it. We know that work is force times distance. Well, we're exerting this force, so what we can do is we can imagine the force here as being this very tiny little bit right here of delta x, okay, and delta x, we exert a force here, and so we can find the work there, the work there, the work there. So really we can think of the work as the integral of the force delta x with the limit of delta x getting very small. And so that we recognize as integral f dx. So really a more general way of writing work is not just force times distance, it's integral f dx. This allows for the possibility that the force might change as you are doing this. So you might not have constant force. If you don't have constant force, the equations we did before where we assume constant acceleration don't hold. This would hold. So this is a much more general form of that equation. Now, if we look at this, integral f dx, well, we know that f is ma. Well, we also know that the mass is going to be constant, so it comes out of the integral. Now, a is dv dt, okay, dx. But wait a minute, we can pretend this is a fraction. Dx, this is going to be dv dx dt. Well, what's dx dt? That's just velocity. So the work is going to be m integral v dv. Well, if we integrate from start to finish, so initial to final, then that would be integral v dv is going to be 1/2 v squared, evaluated initial and final. So that would be that the work is 1/2 mv final squared minus 1/2 mv initial squared. Or we can think of it as our other terminology we sometimes use is 1/2 mv squared minus 1/2 mv naught squared, where that's my initial velocity right there, and this is my velocity at later time. Now, if v naught is 0, then the work done is the total energy that's in there. And in that case, the work done would be 1/2 mv squared. So that's if the initial velocity is 0. So that is the total work, which means that's the total energy. Now, it's moving, v, it's moving. So we would say this is the energy of motion, or kinetic energy. So that's the energy of motion. So that's the work. Remember, work is change in energy. So that means that the energy in this case is going to be just kinetic energy, okay? And the symbol that we have for kinetic energy is generally just K. So we would say that K is going to be 1/2 mv squared. So this is the kinetic energy associated with motion v. Okay, now, your book starts off early in chapter 7 just writing down without any explanation that K equals 1/2 mv squared and doing stuff. And I always thought that was a disingenuous way of doing it because we obviously can calculate where this comes from. It's not just some mystery equation, so I like to show where it comes from. Now, this actually has some interesting things. Remember, we say conservation of energy. So imagine a car, and your car is going to go down the road at some velocity v. And so you want to to get energy to make it go. Where does the energy come from? It comes from gasoline. So it has to come from the fuel. We're ignoring electric cars for the moment, but it comes from fuel. And so, well, even electric cars, it comes from fuel. It's just that you have to use the fuel someplace else and transmit it to the car. Make electricity, you don't have 100% efficiency, so when you go from the fuel to electricity, you lose something. When you transmit it, you lose something. When you charge it and store it in as electrical potential in the batteries, you lose something. And so there's inherent inefficiencies in the process. It doesn't necessarily use gasoline, but it is using fuel, and you're not using 100% of the energy of that fuel, even for an electric car. But what we have here is that we have a vehicle, and we say that the energy largely is going to have to come from some kind of fuel. So there's several things we can tell from this. The faster you go, in general, the more fuel you're going to have to use because you've got more kinetic energy. So a vehicle driving 70 miles per hour is going to use more fuel than a vehicle driving at 50 miles per hour, which uses more fuel than a vehicle driving at 30 miles per hour. Now, there are some catches to this. Typically, when you look at mileage ratings of vehicles, you notice that the highway mileage is better than the city street mileage, and you say, well, that didn't fit because city streets you drive slower. Well, you also stop. And every time you stop, all that energy that you had while you were driving is thrown away in the form of heat through friction in the brakes. I mean, if you don't believe me, you can just stop and reach under the car and grab the brake parts, and you'll never do it again because you'll sear your hands horribly and be horribly burnt. So don't really do that. Okay, but the heat. You are throwing the energy away somewhere, and it goes away typically as heat in most cars. And so every time you stop, you throw away all the energy, then you have to use more fuel to get back up to speed. So city driving is stop, start, stop, start. You have traffic lights, you stop and start a lot. And so that is why you use more fuel in the city driving than you do highway driving, because highway driving inherently it takes more energy to get going. Okay, now the other issue that comes into it is efficiencies of internal combustion engines. They are designed to actually operate most efficiently at certain speeds, and so that turns out those certain speeds are not super slow because people typically don't drive super slow. So they're designed to operate most efficiently at a little bit higher speeds, and so that again, as I'd said in the live session, converting from chemical energy in the fuel into the mechanical energy driving the car is not 100% efficient, and so the engines are more efficient at some speeds than other speeds, and so so what I'm saying here does have some caveats. Mass. The more mass the vehicle has, the more energy it's going to take to go. There's no way around that. That's an absolute ironclad thing. If you've got double the mass, it's going to take double the energy, period. No way, no if, and, or but. It will take double the energy to make it go a certain speed. And there's no way around that whatsoever. If it has double the mass, it will take double the energy. So larger vehicles are inherently going to have lower fuel efficiency than smaller vehicles. Larger electric vehicles are going to drain the batteries faster than smaller electric vehicles. There is absolutely no way around that. It's just going to happen. Okay, now the automakers are under pressure to improve mileage, and so they are working very hard to reduce the weight of the vehicle. So they're trying to make it lighter, make it out of lighter components. Figure out what can you do to make it lighter, in any way possible, because just a tiny bit lighter would over the life of it would have a huge impact. And one of the annoying things they've come up with is, for a lot of vehicles, they leave out the spare tire. because they said, well, normally if you're in the city and you have a flat, you can get it taken care of. I actually typically have a lot of driving out in the country where a flat would be like devastating. So for me, a spare tire is more important than the fuel efficiency. But for other people, maybe not. And so, but that is one of the ways they cut the weight. And of course, if you're driving around with a trunk full of stuff, tools and this, that, and the other that you don't need, then that's going to increase the weight of the vehicle, which increases the amount of energy necessary to get it going, which reduces your fuel efficiency. And so, but anyway, so this gives you an idea of the application of kinetic energy. Okay, we'll be doing a couple more examples here with kinetic energy.